We all know that digital computers changed virtually every aspect of our life. Well, the arrival of quantum computers could be even more historic than that. We're now in the initial stages of the next revolution. We're talking about a new generation of computers, the ultimate computer, a computer that computes on atoms, the ultimate constituents of matter itself. The question is, who's involved in this race to perfect quantum computers? And the answer is everyone. All the big players are part of this race because if they're not, Silicon Valley could become the next Rust Belt. Also, anyone who's interested in security is interested in quantum computers. They can crack almost any code that is based on digital technology. That's why the FBI, the CIA, and all national governments are following this very closely. Quantum computers will change everything. The economy, how we solve problems, the way we interact with the universe, you name it, quantum computers will be there. I'm Dr. Michio Kaku, professor of theoretical physics at the City University of New York, and author of Quantum Supremacy, about the rise of quantum computers. You see, computers have gone through three basic stages. Stage one was the analog computer. So 2,000 years ago, there was a shipwreck. And in the boat that sank was a device, and when you brushed away the dirt and debris, you began to realize that it was a machine of incredible complexity. It was, in fact, the world's first analog computer, and it was designed to map the motion of the moon, the sun, and the planets to simulate the universe. But as we primitive peoples became more prosperous, we had to count things. Count how many cows you had. Count how much profit you made. Analog computers could be based on sticks, bones, whatever it took to count. So this went on for thousands of years until finally we reached the work of Charles Babbage. He creates the ultimate analog computer with hundreds of gears and levers and pulleys, and by turning the crank, you could then calculate longitude, latitude, you could calculate interest rates. It was very valuable to have an instrument like that for the banking industry, for commerce. Then World War II comes along. Babbage's machine is simply too primitive to break the German code, so the job was given to mathematicians like Alan Turing. Alan Turing was the one who codified a lot of the laws of computation into what is called a Turing machine. And of course, it's digital. Now, the digital revolution is based on transistors. It operates on zeros and ones, at the speed of electricity. Every digital computer is a Turing machine. The next step beyond digital computers is the quantum era. Richard Feynman was one of the founders of quantum electrodynamics, but also a visionary. And he asked himself a simple question: how small can you make a transistor? And he realized that the ultimate transistor is an atom. One atom that could control the flow of electricity, not just on or off, but everything in between. We have to go to quantum computers, computers that compute on atoms rather than on transistors. Transistors are based on zeros and one. Reality is not. Reality is based on electrons and particles, and these particles in turn act like waves. So you have to have a new set of mathematics to discuss the waves that make up a molecule. And that's where quantum computers come in. They're based on electrons, and these electrons, how come they have so much computational power? Because they could be in two places at the same time. That's what gives quantum computers their power. They compute on not just one universe, but an infinite number of parallel universes. Now, why am I mentioning this? Because this summarizes the power of quantum computers. Quantum computers compute on parallel universes. That's why they are so powerful. So how much faster is a quantum computer over a digital computer? In principle, infinitely faster. When we talk about digital computers, we can measure their power in terms of bits. For example, spin up, spin down, zeros and one, would constitute 1 bit. For a large digital computer, we're now talking about billions of bits that are modeled by transistors. Except now, quantum computers talk not just about spin up or spin down, but everything in between. That's called a qubit. 1 qubit represents all the possibilities of an object spinning between up and down. Thousands of qubits can now be modeled with the latest generation of quantum computers. Eventually, we hope to hit 1 million. And so we're talking about exceeding the power of ordinary digital computers. That's called quantum supremacy. It is the point at which a quantum computer can outrace and outperform a digital computer on a certain task. We passed that several years ago, but we want a machine that could exceed the power of any digital computer. We're not there yet, but we're very close to it. The number one problem facing quantum computers is the question of decoherence. Everything is based on particles like electrons, and electrons have waves associated with them. When these waves are vibrating in unison, it's called coherence. And then you can do calculations of a quantum mechanical nature. But if you fall out of coherence, then everything vibrates at a different frequency, and what is that called? Noise. You have to reduce the temperature down to near absolute zero, so everything is pretty much vibrating slowly in unison. That's difficult. Now, nature solves this problem. It is the basis of all life on the Earth. Photosynthesis, for example, is a quantum mechanical process. Mother Nature can create coherence at room temperature. Amazing. A flower can do calculations that our most advanced quantum computer cannot. Mother Nature is still smarter than us when it comes to the quantum theory. So let's face it, there are hurdles affecting the growth of quantum computers, but they pale in comparison to the benefits that may be unleashed by quantum computers. We're talking about opening the floodgates. Take a look, for example, of food supply. The green revolution that allows us to feed the population of the world is slowly coming to an end. We're trying to use quantum computers to unlock the secret of how to make fertilizer from nitrogen. Take a look at energy. Quantum computers may be able to create fusion power by stabilizing the superhot hydrogen inside a fusion reactor. And take a look at medicine. You realize that life is based on molecules. Molecules that can create Alzheimer's disease, Parkinson's disease, cancer. These diseases are beyond the reach of digital computers. But hey, this is what quantum computers do. We'll be able to model diseases at the molecular level. And that's why we hope to cure the incurable using quantum computers. We're talking about turning medicine upside down. My personal hope for quantum computers is that we'll be able to create a theory of the entire universe. The theory that eluded Einstein, the theory that would explain black holes and supernovas and galactic evolution. But the equations are so complex that no one has been able to solve them. Perhaps they'll be solved in the memory of a quantum computer.
would the world look like with a computer that could accurately model the laws of nature? That's the promise of quantum computing, but there have always been limitations. Now is one of our longest running research projects. Our team at Microsoft has been able to take a subatomic particle that has only been theorized until now, and not only observe it, but control it, creating an entirely new material and a new architecture for quantum computing. One that can scale to millions of qubits on a single chip.
This is not a work of science, it's a work of science and art.
I gotta be honest, some of these ideas are a little science fiction sounding.
It will solve problems unsolvable by the combined power of all the world's compute today, and promises to revolutionize fields such as medicine, material science, and our understanding of the natural world. Our first quantum processor based on this architecture is the Majorana 1. Yeah, I've always been fascinated with puzzles and challenges and a mixture of mathematics and computers. And so when I learned that there was this type of computer that didn't exist yet, but could solve problems that we couldn't solve with our digital, all of the computers we had, I was just fascinated. I wanted to learn, well, how can I help that computer be built?
Over the years, I ran into problems that I could not solve on the most powerful computers. But then over time, I realized, hey, I could solve that if I had a quantum computer. A laptop can solve a problem of 10 electrons. A supercomputer can solve a problem of 20 electrons. But no classical computer in the world can exactly solve the behavior of 30 or 40 or 50 electrons.
The number 30, 40, 50 electrons, those numbers are seemingly small, but require up to lifetime in the universe timescales to solve with all of the world's computers operating together. That's until you have a scaled quantum computer that can solve these problems efficiently.
These calculations are so complicated that then if the classical computer was as big as this entire planet, it would still not be able to compute it, just to give you a construct of scale. And a quantum computer can do it, and can do it very, very well.
At the core of a quantum computer are these qubits. Qubits are like our classical bits, right? These are essentially zeros and ones in a transistor. And we need the analog of that in quantum computing. The analog is a qubit, a quantum bit, that serves as that core information unit. It's where we store the information and then we process on those qubits to create computation and ultimately, get solutions back out. Now, there's many different ways, right, to create a qubit. The reason quantum computing has been so slow to progress is that the industry has been struggling with problems making qubits reliable and resistant to noise. Progress has been incremental.
The challenge is qubits are actually pretty delicate in general, so you need underlying qubits that are really stable. But you don't want that to come at a cost, because you don't want your underlying qubits to be really big. That's one way to make them more stable, is have them really big. But if they're really big and you're still going to need many of them, then how are you going to fit them all into your system? You don't want to deal with something the size of a warehouse. Then the second thing is you don't want the qubits end up being slow, right? Because if the price you pay for getting something stable is you have to go really slowly, then a computation that might take you a month ends up taking you a decade, and then it's not useful. People in the early days of computation used vacuum tubes, and then that technology, actually you could build very good computers with it, and then the transistor was invented, and the earliest transistors weren't necessarily that great, but it became clearer over time as the transistor developed and the integrated circuit developed that this was going to be the technology of the future. In that spirit that the first generation of qubits may not be what gets us to the next stage where we can really solve the kind of problems I was mentioning that are really important. And so we might need to invent a material and therefore a quantum processing unit that has the right properties. So for us, we want something that has some built-in level of error protection. And a lot of those ideas actually were explored in the context of software, of quantum error correcting codes, but you can actually build a lot of those ideas into hardware.
So the way you design that qubit matters. We see the states of matter every day. Solids keep their shape, liquids vary but keep their volume, gases expand to fill the space they're in, all defined ultimately by how their atoms behave. But what if there were more? What if, under the right conditions, you could engineer more? States that have only ever been theorized, that would change how subatomic particles actually behave? 100 years ago, mathematicians predicted one such new state of matter, the topological state. And since then, researchers have been looking for a very specific, very useful quasi-particle within it, the Majorana particle. Last year, we were able to observe it for the first time. And this year, we're able to control it and use its unique properties to build a topoconductor, a new type of semiconductor that operates also as a superconductor. With this material, we can build a whole new foundational architecture for our quantum computers, a topological core, allowing us to scale to not tens or hundreds of qubits on a chip, but millions, all in the palm of your hand.
Majorana's theory showed that mathematically it's possible to have a particle that is its own antiparticle. That means you can take two of these particles and you bring them together, and they could annihilate and there's nothing left. Or you could take two particles and you bring them together and you just have two particles. Sometimes it's nothing, the zero state, and sometimes it's the electron, the one state.
So it really has taken quite some thinking, right? Some time to design a device, design a chip that can enable measurement of this literally elusive particle. We've designed a chip that is able to measure the presence of Majorana. Majorana allows us to create a topological qubit. A topological qubit is reliable, small, and controllable. This solves the noise problem that creates errors in qubits. Now that we have these topological qubits, we're able to build an entirely new quantum architecture, the topological core, which can scale to 1 million topological qubits on a tiny chip.
Every single atom in this chip is placed purposefully. It is constructed from ground up. It is entirely a new state of matter. Think of us as building the picture by painting it atom by atom. In a regular chip, the computation is done using electrons. We don't use electrons for compute. We use Majoranas for computing. It's an entirely new particle. It's half electron.
When we look at the design of this chip, right, first of all, you can fit so much on just a small form factor, right? This chip can store over 1 million qubits, right? Over 1 million can fit on just this small form factor. In addition, we don't want to wait centuries or millennia for a solution. And so this chip also offers the right speed to get solutions from the chip in a reasonable, efficient, amount of time. That's the beauty in this qubit design, the topological qubit. It has the right size, the right speed, and the right type of controllability. And all of that together means that it has an ability to scale like no other.
The way the system that we are constructing works is you have the quantum accelerator, you have a classical machine that works with it and controls it, and then you have the application that essentially goes between classical and quantum depending on which problem it's trying to solve. Once the computations are done, the results are resynthesized on the classical side and produced back to the user as one complete answer. Where the quantum machine shines, it is able to do simulations, particularly in chemistry and materials, that are extremely accurate as an actual wet lab experiment. Imagine a world where a scientist computes the material that they want, and they compute it to the accuracy that it's first time right. So when you walk into a lab, you don't need to experiment anymore. Imagine a battery that you charge it once and you never have to worry about discharging.
What can you do with 1 million qubits? In the last few years, there's an explosion of artificial intelligence, right? Co-pilots. And what's so inspiring about a quantum computer is that with a quantum computer augmenting the AI capability, it can help more, drive even more discovery.
What makes me excited about quantum computing is that it will give us the tool to tackle many of these challenges at the fundamental level by creating new chemicals, new drugs, new enzymes for food production.
Honestly, it's kind of mind-blowing right now because this is something we've thought about for a while, years or more.
We call the ages of mankind by materials. We've talked about the Stone Age, we've talked about the Bronze Age and the Iron Age, the Steel Age, the Silicon Age. Materials define our culture, define our mankind, define our progress. Thus, what could be more powerful than having a machine that can let you radically change the way we work with materials?
Our leadership has been working on this program for the last 17 years. It is the longest running research program in the company. And after 17 years, when we are showcasing our results, we are showcasing results that are not just incredible, they're real. They are real because they will fundamentally redefine how the next stage of the quantum journey takes place.
We're at the cusp of a quantum age, and Majorana 1 is just the beginning.